Hi guys, I'm Monica. I welcome you all to my channel Aerokar. So in this video we will be now starting with the fundamentals of incompressible and inviscid flows, wherein we had discussed the types of flows in our previous videos. One of them was the incompressible flow and inviscid flow as well. So we are going to combine these two types of flows together, that is inviscid and incompressible, and have a discussion on them and see what do we get up to as we proceed with our discussion. So in the discussion of inviscid and incompressible flows, first we start with the most used or most talked about equation, which is the Bernoulli's equation. So without any further delay, let's get started. What does this Bernoulli's equation do? It relates velocity and pressure from one point to another point in an inviscid incompressible flow. So generally some aircrafts, they fly below 134.11 meter per second, right? So in such cases, this Bernoulli's equation, or the case of inviscid incompressible flow, comes into picture. And in addition to these low speed aircraft applications, the first one where we can see this application of Bernoulli's equation is the first one. We can say it as low speed aircraft applications, where the aircrafts are flying at low speed. Other than the aerospace applications, we also have other applications. So what are those? One is water flowing through a pipe. This is the example that we have. Then next we have motion of submarines and ships. So when the submarines or ships are moving through water, in such cases also we use the Bernoulli's equation. And the fourth one would be design of wind turbines. So in the designing of wind turbines also we use this Bernoulli's equation. Now, for most of the part of this incompressible inviscid flow, what happens is there are some terms that we ignore, or the effect of some terms. That is, the first is friction, then the next would be thermal conduction, or also known as diffusion. So these effects, or the effects of these terms, are neglected. The fluid in which these terms, or the effect of friction or thermal conduction, is neglected are known as inviscid incompressible fluids, okay, or inviscid incompressible flow. Now we also call this inviscid incompressible flow as ideal flow, and if we call it as a fluid, then it will be an ideal fluid. Yes. So proceeding with our derivation for Bernoulli's equation. Now what we are going to do over here is we are going to consider the x component of momentum equation, which we had previously derived. So some of you might be recollecting the x component of momentum equation. So let us write it down. What is it? So now this is the x component of momentum equation that we had derived previously. What if I say for an inviscid flow, that is, we are considering inviscid flow over here, right? Which means if I say inviscid flow, what would be the condition for inviscid flow? My viscous forces are equal to 0, which means this F viscous goes to 0. And the second condition, what am I putting over here? With no body forces. So as we had seen in the derivation, Fx was denoting the body forces, which means this also goes to 0. So what am I left with after this? Rho du by dt is equal to minus dou p by dou t. Now, if I am supposed to elaborate this a little, how can we elaborate that equation? How can we write it? So when I elaborate the equation, this is how I can write, that is elaborating this derivative du by dt. Let us say this is our equation 1. Now this equation we have obtained for an inviscid flow and when there are no body forces. Now if I say one more condition, that is steady flow. Now when I say steady flow, which means dou rho by dou t goes to 0, or any term with respect to time goes to 0. So what are we left with upon applying this condition? We are left with u dou u by dou x, v dou u by dou y, w dou u by dou z, which is equal to minus 1 by rho dou p by dou x. Right. So because the reason we are getting rho over here is, here we have dou u by dou t, correct? So this term goes to 0. And where is this rho coming from? From these terms, that is rho becomes common and we take it on this side. So that is why rho is coming into picture over here. Now let us say this is our equation 2. Now what if I multiply this equation 2 by the term dx? So if I multiply this by dx, what is the equation that you get? U dou u by dou x dx plus v dou u by dou y into dx plus w dou u by dou z into dx is equal to minus 1 by rho dou p by dou x into dx. Let this equation be in the same state for a while. Let us say this is our equation 3. Now let us consider flow along a streamline in a three-dimensional space. So we know the equations for the streamlines, right? For a three-dimensional space, what are those? W dy minus v dz is equal to 0. U dz minus w dx is equal to 0. And the last one would be v dx minus u dy is equal to 0. So let us name these equations as A, B and C. Now our task is to substitute two of them, that is B and C. So we are going to substitute B and C in equation number 3, that is this equation. So upon substitution and mathematical manipulation, the final equation that we get is, so this is the equation upon substituting B and C in equation 3 and manipulating it. So let us say this is our equation 5. Equation 4 would be the one which you get on direct substitution, so which is, you can try. And this is upon the mathematical manipulation. I've written the direct equation. Now let us say that u, I can write u as a function of x, y and z. So how can we write the differential of u, that is du? If I substitute this term in equation 5, that is over here, which represents du, correct? So what will happen to equation 5? Can I write it as u du is equal to minus 1 by rho into dou p by dou x into dx, correct? Or maybe we can also write it in one more form, that would be this. This is the second form which you can write the equation in. Let us say this is our equation 6. Remember this equation 6. Now what is the y component of equation? Y component of momentum equation. How can we write that? That would be rho dv by dt is equal to minus dou p by dou y plus rho fy plus fy viscous, correct? Similarly, if I do the same thing, that is of assuming inviscid steady flow for this equation, for this particular equation, if I say we have inviscid steady flow. So when I say this equation has inviscid steady flow, it would be of this form. Let us say this is our equation 7. Now similarly for the z component, I can write it as d of w square, which is equal to minus 1 by rho dou p by dou z into dz. Let us say this is our equation 8. Now, upon adding these three equations, that is, if I take the total of equation 6 plus 7 plus 8, alright. So, upon adding these three equations, what do we get? Just have a look. 1 by 2 d of u square, v square, w square, which is equal to minus 1 by rho in common, minus dou p by dou x dx. Oh, the minus gets eliminated over here because it is already taken outside. Dou p by dou y dy plus dou p by dou z dz. It would be y over here. It would be y. So let us say this is our equation 9. Now, one thing we know is I can write u square, v square, and the sum, this thing, as v square, that is the magnitude of velocity, correct? Let us say this is our equation 10. So, and one more thing, how can I write this term as the inside bracket term, that is dou p by dou x dx plus dou p by dou y dy plus dou p by dou z dz. Can I write this as dp, right? With the, according to the definition, it can be written this way. So now I will substitute this 10 and equation 11 in equation 9. So what do we get here? Substitution, this is how I get the equation, or this can also be written as dp is equal to minus rho v dv. Alright, so this can be written in this form as well, and let us say this is our equation 12, which is known as the Euler's equation. So this is known as our Euler's equation. This equation 12, that is the Euler's equation, where do we apply it, or where can we apply it, in what cases can we apply it? So we can apply this Euler's equation. The first condition would be that the flow is inviscid. Secondly, there are no body forces. So when these conditions are satisfied, we can say that the Euler's equation, this particular Euler's equation, that is equation number 12, what we have derived, is applicable. And when you look at the equation, what does it tell? What does it relate? It relates to the change in velocity along a streamline to the change in pressure along the same streamline. Okay, so now if I say, now comes the condition for incompressible flow. That is, now let us put the condition that the flow is incompressible, which means my density would be assumed to be invariable. That is, the changes in density are negligible, are so small that they are negligible. That is where we assume that the rho, which is density, is constant, and this kind of fluid we call it as an incompressible fluid, which we had already studied. Now, so for an incompressible flow, what we are going to do is we are going to integrate this above equation between points 1 and 2 along a particular streamline. So if I integrate the above equation, which is P1 to P2, dP is equal to, rho comes outside because it is constant, and we get V1 to V2, V dV. So upon solving this equation and performing the mathematical manipulations, this is the equation that we get. So let us say this is our equation 13, which is the Bernoulli's equation. Now, the question about Bernoulli's equation, where is this equation applicable and how can we use it? Let us have a look. Before we look at the application and using part where we can use this equation, by looking at this equation, what we can tell is along a streamline, it relates to the point P1 and V1, that is P1 and V1 are velocities at point 1 and P2 and V2 are velocities at point 2 on the same streamline. So I can also write this equation as P plus half rho V square is equal to constant along a particular stream line. So let us say this is our equation 14 and this is along a streamline. Okay. Now, if I say that my flow is rotational, so what happens for a rotational flow? The value of constant, so here it would be the value of constant in the streamline in the equation 14 that we have derived over here. So the value of this constant will change from one streamline to another if my flow is rotational. This is for the rotational case. And on the contrary, if the flow is irrotational, then what would happen? Bernoulli's equation holds between any 2 points in the flow, and that is for an irrotational flow. So basically, for an irrotational flow, I can write the equation as the same, that is P plus half rho V square is equal to constant, and this would be 15, but this would be throughout the flow, that is at any point in the flow, not necessarily for a particular stream line. This was the derivation of the Bernoulli equation. Now, what is the physical significance of these equations, that is equation from this equation, that is equation 13 to equation 15? What is the physical significance that we derive from these equations is that as the velocity increases, the pressure decreases, and as the velocity decreases, the pressure increases. Now, this equation, the Bernoulli equation, was derived from momentum equation, which means it is a statement of Newton's second law for an inviscid incompressible flow. So I can call it as a Newton's second law, the statement of Newton's second law of momentum, that is the momentum equation, but for inviscid incompressible flow. So this Bernoulli equation, it is also a relation for mechanical energy in an incompressible flow. What it states that the work done on a fluid by pressure forces is equal to the change in kinetic energy. So if I take this on this side, so what will it suggest to me? If you look at this form, probably, or maybe even at this form, it suggests that whatever the change in pressure, whatever work is being done on the fluid by the pressure forces, it will show me what is the change in kinetic energy of the flow. So this is all about the Bernoulli equation. We will discuss furthermore interesting topics with respect to inviscid incompressible flows and what all different various topics come under inviscid incompressible flow when we talk about the aerodynamic study. Thank you for listening. Stay tuned.